Okay, now that we've finished shear force diagrams, the next one to look at is a bending moment diagram. And the clue is in the title. We're looking at the bending moment across a beam, or a bit of metal, part of a bridge, an axle. So we'll do the same thing. We're going to have three cases. We're going to have this one's going to be a beam with 2-point loads. We're going to have one with just a UDL, and then we're going to have the same one with 1-point load and a UDL. So I'm using the same beam examples as I've done previously to save a bit of time with working out the reactions. So this question, bending moment diagram. So we need to plot now the bending moment across this beam. So very similar to shear force. We'll work out the reactions first, and then we'll start from the left hand side of the beam and work out the bending moments at certain points. X equals 2, X equals 3, X equals 4, whatever. And then we'll draw the bending moment diagram and we locate the maximum bending moment. Now if you remember, zero shear force is where maximum bending is. So we'll be pointing that out soon. So here's my beam. We've seen this before because we drew a shear force diagram of this. 4 kilonewtons coming down there, point load. 3 kilonewtons coming down there, point load. No UDL, which makes things a bit better for us. No UDL. Don't forget that UDL can be the weight or it can be something on the beam. So we haven't got any UDL, which makes it a bit easy for us. So draw the bending moment diagram for the beam, calculate reactions first. So we need to calculate the reactions. Now, as in pure Blue Peter style, we've done that earlier. So we've done that in the previous example. When we did the shear force diagram, we worked out the reactions for these. So in your assignments or in questions, you're going to have to work these out, but we've done them previously. If you can't remember how to do that, I suggest you going back and watch that video and work out the reactions. Because if you get these wrong, everything else is going to be wrong. So you need to make sure. So these are the reactions. 4.4 there, 2.6. Don't forget, whatever's coming down is going up. So we've got 4, 5, 6, 7 coming down, and we've got 7 coming up. So now we've got the reactions. So now all we've got to do is work out the moment at certain points along the beam. Now we know that a moment is force times distance. A moment is force times distance from a previous life. So what we're going to do is we'll look at the moments at, say, x equals 0. Well, we will do that. Then we'll go 2, 4, 6, 8, 10 perhaps to work out the bending moments at each of the points. And then we'll draw a graph. And then we'll find out where the maximum bending moment is. The maximum bending moment is where failure is likely to occur due to bending, so it's quite an important point. So, starting from the left, let me get a highlighter. Let's use green because it's better for the environment. Starting from the left of the beam, so moment is force times distance. So all I'm looking at is force and distance. Starting from the left, so when I'm here, what can I see? Force times distance. Obviously, I can see a force, which is 4.4. My distance, I'm x equals 0. So my distance is going to be 0. So 4.4 times by 0 gives me 0. So that's a good start. And then I'm going to go x equals 2. So what I've done now is I've come in x equals 2. So now what moment is here? Forget what I see along here. Ignore what I see along here. Ignore this. Right? It's just what I can see here. So force times distance, I can see this force, and I'm now 2 meters away from it. I can see this 4, but I'm directly below it, so I'm not There's no moment produced by that 4 because it's pushing on the point. It's like trying to open a door on the hinge. It's not going to work because there's no distance. So 4.4 times by 2, 0 and 2. Look, I'm 2 meters away now from the 4.4. It's trying to go clockwise, look. So I'll have a positive. This one's trying to go anti-clockwise. It's 4 times by the distance. Well, we're directly below it, so there's the force, there's the distance. So there's no moment produced at that point yet. There will be in a bit. Once we get past the 4, there will be. So at x equals 2, I've just got this, sum of the moments. So in your calculator, 4.4 times by 2. That's going clockwise, so it's positive. This one's going anti-clockwise. Obviously, 4 times 0 is 0, so 8.8, don't forget the killer, because these are all killer. So at x equals 2, 8.8 kilonewtons per meter. So we can plot that point in a bit. I'll now go to x equals 4, just for a laugh. So at x equals 4, I'm about, I'm here, there's 2, so I'm here somewhere. How long is the beam? So it's here somewhere. So it's there, look. So I'm just looking what I can see here. I can see this 4.4. That's still going clockwise, and I'm 4 meters away from it. I can now see this 4 because I'm 2 meters away from it. So I'm going to see that. It's going to go anti-clockwise, so I'm going to have a negative number there. So it's going to be 4.4 times by 2, and then it's going to be 4 times by 2 going anti-clockwise. So sum of again, look, we're adding them up. So if you notice, 2, 2, 4, 4, and these go up in 2s now as well, look. So that's the force, 4.4 times by 4, that's going clockwise, and then this 4 is 2 meters away from where I am. So I'm here, so I'm 2 meters away from this 4. Hence, I got 4 times by 2. So in your calculator, do that. 4.4 times by 4. This one's going anti-clockwise, so we'll take it away. 4 times by 2, because we're adding up. We're not adding up really, but we'll work out the moments at that point. Gives me 9.6. Don't forget the killer. So 9.6, so it's going up. So there's more of a bending moment there than there is there. 2, 4, let's go to 6. The reason 6 is important is because if you remember, we did this example, shear force diagram for this example, and I'll scroll down because I put it down here. Look, so this was the example we did for shear force, and when we did it, we worked out that at x equals 6, there was 0 shear force. So 0 shear force means it's maximum bending moment. So at x equals 6, I'm going to plot a point. I'm going to work a point out because I'm expecting at x equals 6 the biggest bending moment on the beam. And like we said previously, that's where failure may occur. So that's why I'm going to do x equals 6. That's why it's a good way always to do the shear force diagram first, because the shear force diagram, if you're correct, will highlight to you where the maximum bending moment is going to be, and then you can then make sure you work out the bending moment at that point. In our case, it's going to be x equals 6. From that point, it should be getting less. So x equals 6. So all I can see now is what I can see at x equals 6. At x equals 6, I can see x equals 6, I'm there. 4 and 2 is 6. So I can see this 4.4 again, 6 meters away from it, it's going clockwise. This 4 kilonewtons is now 4 meters away, is trying to go anti-clockwise. This 3, I'm directly below it, so there's no distance, so there's no moment produced by it. So it's times by 0. So I've got 4.4 and 6, and I got 4, and I've got 4 and 3 and 0. So x equals 6 as my 4.4 times by 6. If we notice, 2, 4, 6, 8, 10. 2, 4, 6, 8. So at 6, 4.4 times by 6, and then I'm now 4 meters away with the 4 kilonewtons. And here's my 3, I'm directly below it, so there's no distance, hence 0. Anti-clockwise, clockwise, so put all that in the calculator. 4.4 times by 6, take away 4 times 4, take away, I'll put it in, but you don't need to. 3 times 0, 0, so that gives me 10.4 kilonewtons per meter. Don't forget kilo. This now is going to be, if everything's correct, the maximum bending moment, because we know at x equals 6 there's 0 shear force, which means there's going to be maximum bending. So 10.4 is our maximum bending. At that point on the beam, that's where maximum bending is, which means that's where failure due to purely bending may occur. Here. So at this point, that is where things could get interesting. The reason I've done x equals 6 is because at x equals 6 it was 0 shear force, and 0 shear force is where maximum bending is. So from now on, the moments should be coming down, which they are. So make sure you still do it, just to make sure. At x equals 8, all it's going now is, look, is everything's going up by 2, up by 2, up by 2. Because now I'm 8 meters in. I'm 8 meters in, which is 4, 5, 6, 8. I'm there somewhere. So I can still see the 4. I'm 8 meters away from it. 4, 5, 6, 7, 8. There's my 4. I'm about 6 meters away from it, and now I'm 3 meters away. Sorry, 2 meters away from the 3. Clockwise, anti-clockwise, anti-clockwise. So there's my 8. So I'm 8 meters away from the 4.4. I'm 6 meters away from the 4 kilonewtons, and I'm 2 meters away from the 3 kilonewtons. Don't forget it is kilo. So once you get things going, you can just go up by 2s or 1s or whatever you want to do. Obviously, if you went up in 1 meters, you get more points and the graph is a bit more accurate. But really, this is the point we're after. So once you've got the main point, alright, that's all that matters really. So 4.4, we'll put that in, times by 8. I'm hoping it's going to come down now because we've reached the point of maximum bending. Times by 3 times by 2. Let's just put a bracket in there just in case, because you never know. 5.2 kilonewtons per meter. That's all good. And then x equals 10 is all of it. Now with a beam, simply supported beam like this, like with no overhang, we expect the moment to be 0 at the reaction. So 0 here and 0 here. So there's one way of checking. If it comes to 0 at the end, if it comes to 0 here, then you know you're correct. Obviously, if it's slightly more or less than 0, just means your rounding is slightly out or you're rounding errors, so don't be too panicky. So at x equals 10, don't forget I've got this 4.4 times by 10. I'm going to have this 4 times by 8. The 3 times by 4, and I'm also going to have this 2.6, but because I'm here, it's going to be times by 0. Hopefully it comes to 0. So x equals 10, 4.4 times by 10, 2, 4, 6, 8, 10. 4 times by 8, 2, 4, 6, 8, and then 3 times by 4, 0, 2, 4. There's the 2.6, which is this. Don't forget it's coming up really, but because we're directly below it or above it, depending on how you think, it's 0. So hopefully it all comes to 0, which it does. That's one way of checking things. If it came to something like 0.01 or something like that, don't worry too much. It's just that these here, if you've rounded these up, then it's going to knock on. So just put it in your calculator because it does come to 0. 4.4 times by 10. 4.4 times by 10. These are all anti-clockwise. Just stick them in. 3 times by 4. Don't forget the minus. Plus, because this is coming up, trying to go. So it doesn't really matter really because it's times by 0 anyway. So 0. 0. So that's one way of checking to see if your reactions are correct and your bending moments are correct because it comes back to 0. So this makes a bit of sense to me because we worked out the maximum bending moment was x equals 6 and our shear force diagram of the same problem. So yes, I'm quite happy that we're correct. Now all you've got to do is plot these numbers. So plot now, bit of graph paper or pencil and ruler, x equals 0, plot 0, x equals 2, 8.8, x equals 4, 9.6. 6 is going to be 10.4, 8 is going to be 5.2, 10 is going to be 0. Don't forget the killer. So here's my graph. So we're going to start off from 0 and we're going to go up to about 10.4. So make sure you can fit that in. And we'll go up to 10 on the x-axis. So 2, 4, 6, 8, 10. I've gone a bit more just to get it in. There's the units, include units. Bending moment, kilonewtons, don't forget. Title perhaps, bending moment diagram title. I've gone to 12 because we need to go more than 10.4. So then x equals 0 and 0, so x equals 0 and 0. And then 2 is 8.8, so there's 2 and there's 8.8. Use a ruler if you haven't got any graph paper. 4 is 9.6, so 4 is 9.6. Plot the point, put the numbers in. X equals 6 is 10.4, 6 and 10.4. Hopefully this is the top of the curve, which it is, so 5.2 is x equals 8, so it's coming down, so 8, fairly strict coming down now, straight coming down, and then 10 is 0. Thank you very much. Bang. So there's all the points plotted. Obviously I've used a ruler there and I've used my hand there because it is a curve. I would then label this, so draw a line, maximum bending moment of 10.4 kilonewtons per meter at 6 meters from the left, so 6 meters from here, or 2 meters from the right. Shear force diagram of the beam shows 0 shear force at 6 meters from the left, which it does look because we did that previously. So the shear force diagram and bending moment diagram work out. 0 shear force equals maximum bending moment. What you could do is you could plot this graph and this graph on the same graph paper, and as long as the scale is correct, you can then just draw a line down just to make sure that they meet. So that's nice and easy. It's a bending moment diagram with 2 point loads, no UDL. Like I say, we did the shear force first just to find where the 0 shear force is, and that's where the maximum bending moment is. Plot the graph, label it, and all we're doing is looking at certain distances what the moment is at that point. So that one is a bending moment diagram with 2 point loads. So it's not too bad. Normally you'll get a question, it'll say something like, here's a beam, draw the bending moment diagram and shear force diagram. So normally you'll do 2 diagrams. So that's that one. The next one was going to be a bending moment diagram with the UDL in it. So I'll use the same one as I did before with the UDL. So that'll be coming shortly. Don't call me shortly. Over and out.